Hello everyone, myself N. Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So in the previous session, we've gone through the derivation of shear flow in open section beams and we derived the formula for it. And now we are going to use the formula and for solving the problems on shear flow of open section beams. So let's consider the problem which is shown here, and so the question, determine the shear flow distribution in the thin walled Z section shown in figure due to a shear load Sy that is applied through the shear center of the section. So when the shear load is applied shear center of the section, and we know that the twist of the section must be 0. So twist of the section must be 0, and corresponding, so the shear load must apply through the shear center of the section, okay, in such a way that the twist will be 0. So the problem here in this is asking to calculate the shear flow distribution for the thin walled Z section. So you can see this Z section, and the foremost thing is nothing but we'll need to remember the formula. So it's a Z section which is given, and it has got two flanges. One is lower flange, one is upper flange, and one is a web. And you can see the dimensions also. Width of panel 1 to flange 1 2 is taken as h by 2, and similarly for 3 4 also h by 2, and height is taken as h from 2 to 3. And by the inspection of this Z section, even we've seen in the last sessions also that the centroid will lie over here. It is not symmetrical. So the first thing what we have to understand is the given section is an unsymmetrical section. Okay, so for this unsymmetrical section, first thing you have to do is nothing but you have to calculate the position of centroid or center of gravity. So but for this, even though it is unsymmetrical, by the lengths that have been distributed on the upper and lower surface, lower surfaces, so that you can assume that the centroid lies at the center of this section. Okay, so therefore no need to calculate the centroid for this problem. So first, since we need to calculate the shear flow distribution, and I hope you remember the formula for shear flow distribution, that is Qs is equals to minus Sx Ixx minus Sy Ixy divided by Ixx Iyy minus I square xy into integral 0 to s t into x into ds, okay, minus sy Iyy minus sx Ixy divided by Ixx Iyy minus I square xy integral 0 to s t into y into ds. Okay, so this is a formula which we use for shear flow in open section beams to find out the shear flow distribution. Okay, so if you look at the given data, and he has given Sy is applied through the shear center. So Sy you can consider as Sy, which is applied here, that is given, and since the horizontal shear load is not given, you can substitute it as 0. Okay, and since the given section is unsymmetrical section, it is not symmetric, and the product of inertia is also not equal to 0. So you have to find out moment of inertia Ixx Iyy along with that Ixy first for the analysis. So to start with the problem of the shear flow in open section beams, one should find out the moment of inertias Ixx Iyy and Ixy. Before that, we need to calculate the centroid position also, but since for this diagram the centroid lies over here by the inspection, so therefore no need to find out the centroid. Straight away you can move on to calculating the moment of inertias for this particular problem. Okay, otherwise first you have to start with the centroid position, and then you have to move on to the Ixx Iyy and Ixy moments of inertias. So in this you can substitute Sx equals to 0 here, Sx equals to 0 here, that from the given data. Okay, rest of all the things we need to calculate. So the foremost thing is what? Ixx Iyy and Ixy we need to calculate, Iyy. Okay, so to go with this one, first let's try to understand this. So this is a formula for shear flow in open section beams, and after substituting Sx equal to 0, which is given, the formula is reduced to over here, and then here what we need to understand is you need to calculate moments of inertias. So the calculation of moment of inertia is very important for us. So let's make an eye of calculating the moments of inertia over here. Okay, so in the last problem also we have seen how to calculate the moment of inertia for the z section, and when we solve the direct stress distribution formula, and here also it's very important. So for analysis, what we are doing here, we are trying to find out two elements, that is 1 to 2 and 2 to c we are going to consider, and we are going to try find out Ixx for this. So as you've seen that Ixx is the combination of Ixx 1 2 plus Ixx 2c, and which should be multiplied by 2 because you got another upper half of the section which is symmetrical. Okay, so Ixx, that is equals to, and for Ixx 1 2, and if you try to take 1 2, so what is the formula? Ixx equals to, usual general formula is Ig plus A into y bar square, that you have to use. Okay, so this is a formula which we have to use over here. So Ig, that is moment of inertia about its own centroid, so BD cube by 12, and this Ig is nothing but again BD cube by 12. So that we are going to here. So B here it is h by 2 into d cube, depth is nothing but the thickness divided by 12 plus area of this 1 2 is h by 2 into t into y bar square. Now what is y bar? The distance. What is y bar? The distance from the first figure centroid to the total figure centroid. So from here to here is nothing but y bar, which is nothing but what? H by 2. Half of the distance, that is h by 2. Okay, so here you are writing h by 2 whole square. Okay, plus next for this 2C panel, next for this 2C web, what we are going to do is, first you are going to apply BD cube by 12. Okay, so what is that BD cube by 12? So B is nothing but the thickness, B, that is T, into depth is nothing but h by 2. So you are going to write h by 2 whole cube by 12. Okay, plus area is nothing but again T into h by 2 into y bar square. Now what is the y bar square for this one? So the centroid for 2C is here and the total figure centroid is here. So you need to get the distance from here to here, which is nothing but half of this distance, which is nothing but h by 2 by 2, that is h by 4. So y bar is nothing but h by 4 here. So therefore you have to write y bar square, so h by 4 whole square, that you have to write. Okay, so this is the equation that you are going to write, and it should be multiplied completely by 2, because that 2 when you multiply it gives for C to 3 and 3 to 4 also. Clear? So this is how we calculate moment of inertia about x-axis, and when you try to calculate this, before you calculate this, here there is a term t cube term is there. So this t cube term for the thin wall approximation you can make it to 0, and you left with only these three terms, and in which you can try to calculate here, and you are going to get, when you calculate this, you are going to get th cube by 3. Okay, so here t into h cube by 8, and here you are going to get t into h cube by 8 into 1296. Here you are going to get t into h cube by 16 to 32 you are going to get. Okay, so when you take LCM, you are going to get Ixx equals to th cube by 3. Okay, that is how you calculate moment of inertia about x-axis. And if you try to look into moment of inertia about y-axis for the same 1 2, so similarly, but what you are going to get is Iyy for 1 2 plus Iyy for 2c you have to write, and it should be multiplied by 2 for the rest of the panel, that is C to 3 and 3 to 4. So if you try to write Iyy for the first 1 2, it is dB cube by 12. So d is nothing but t into b cube, that is h by 2 whole cube by 12 plus area t into h by 2 into x bar square. X bar, now what is x bar? The center of first figure is here, total figure center is here. So this is the distance x bar, that is nothing but what? Minus h by 2 by 2, that is minus h by 4 whole square. Okay, this is h by 2 and this is minus h by 4 whole square, plus for the second one, if you do, if you see dB cube by depth is nothing but h by 2 into depth is nothing but width is nothing but t, dB cube by 12, that you are going to get the first term, plus area h by 2 into t into x2 bar square. X2 bar means this is the second figure centroid and this is total figure centroid. There is no distance, horizontal distance between these two. This is pure lying on the vertical plane. So there is no vertical distance. So you can substitute it as 0 and multiply by 2, that you should not forget. Okay. And out of these three terms, this term is 0 and this term also, it's t cube containing term. For the thin wall approximation, you can make it to 0 and you left with only this term. So what is this term? T into h cube by 8 into 12, that is 96, plus here you are going to get t into h cube 4 square 16 plus into 2, that is 32, multiply by 2. And this further, if you try to multiply 2 inside, you are going to get 48 plus th cube by 16, and you can take LCM as 48 easily and you will get th cube, and here you are going to get 3 th cube, and this which you are going to get 4 th cube by 48, which is equals to th cube by 12. Okay. So IYY you are going to get th cube by 12. So IXX you got th cube by 3 and IYY you got th cube by 12. And next you have to find out IXY. Okay. So IXY also you can consider in the similar manner, and you are going to get we will see that also. IXY again is a combination of IXY for 1 2 plus IXY for 2c, and you can multiply by 2 and you can write this IXY for 1 2. Area, that is t into h by 2 into x bar. X bar is nothing but again this one minus h by 4, and y bar is nothing but from here to here, that is h by 2 plus for second one area is again t into h by 2 into its x bar is 0 and its y bar not required, it should be multiplied by 2. So here you are going to get t into h cube by 16 multiplied by 2, and thus you are going to get th cube by 8. So that is IXY. Okay. So not in every class we don't really find out moment of inertia, so that you have to do on it your own, because the moment of inertia you've been learning from starting of the year of engineering, that is engineering mechanics, and followed by mechanics of solids. You should be in a position to quickly calculate moments of inertia, because our problem is not to find out moment of inertia in this problem, but to calculate the shear flow distribution. So our main aim is to find out the shear flow distribution, but for that moments of inertia are required. So you need to complete very quickly moments of inertia to go into the actual problem of finding the shear flow distribution. Is that right? So now after knowing the shear flows moments of inertia, IXX equals to h cube t by 3, IYY equals to h cube t by 12 and IXY equals to h cube t by 8, you are going to take them and substitute in the formula for shear flow distribution in place of IXY, IXX, IYY, IXY everywhere, and then you are going to reduce the form of the equation. Okay. So when you substitute all these and you try to reduce the form of the equation, you are going to get the distribution like this. So QS equals to minus SY by H cube integral 0 to S 10.32x minus 6.84y ds. So this is the shear flow distribution. Shear flow distribution, what we got, and this is a general equation, and now we have to extend it for panel 1, 2 and 2C, so that it will be same like 3C as well as C3 as well as 3, 4. Okay. So to do that, what you are going to do is, first you are going to find out bottom flange. So what you are going to do here is very important to understand here. First you are writing for 1 2, okay, and you have to consider the distribution as S here. Very important here, this to understand. So first what you are doing here, this is h by 2 length, okay. So this is the equation. That means you should know what to substitute for x and y. So first you are considering bottom flange 1 2, and in which you assumed the distribution as S here, okay. And now what to substitute? So for flange 1 2, what is to substitute for x? X is nothing but from the centroid you have to measure the distance. So if S is from here to here, you should know what is the distance from here to here from the centroid. That is what is nothing but x, okay. But what is the distance? First of all, it is a negative distance. So first you have to write minus, because left side of the centroid you will take it as negative. So minus, and total distance is h by 2. You have to subtract this s distance. So minus of h by 2 minus s. You can consider s1 also, s1, okay. So that is the distribution you have to substitute. And for y, what do you substitute? Y is nothing but, again, even if you consider the distribution s, y is nothing but from here to here, it is a constant distance. So straight away y you can consider it is below the x-axis, because this is the x-axis. So below the x-axis from here to here is nothing but y distance. So y you can consider straight away minus h by 2, okay. So that is what here, y equals to minus h by 2 and x equals to minus h by 2 plus s1 from this one. So these two you need to go and substitute in the equation 2 over here, okay. So when you try to substitute here in place of x, so what you are going to get here is minus h by 2 plus h1. This you can substitute. Qs equals to sy by h cube integral 0 to s 10.32. In place of x you can substitute s1 minus h by 2 minus 6.84. In place of y you can substitute minus h by 2 into ds1, okay. Now after this you need to integrate. So sy by h cube 10.32 into s1 integration becomes s1 square by 2 minus h by 2 integration, you are going to get h by 2 into s1 minus 6.84 by 2, or minus into minus you can write plus, and h also you can write, and ds1 becomes s1, okay. So this is what you are going to get for q12 when you substitute 1 2, okay. So q12 distribution, again you can put it in the form, and you can write this as 10.32 s1 square by 2, which you are going to get 5.16 s1 square, and this 2 minus h by 2 into s1, 6.84 by 2 into h into s1, and you can try to reduce this form of the equation, and you are going to get here, so 6.84 by 2 you are going to get 3.42, and again you got minus half, that is 0.50, and you can reduce this form of the equation and just go through this calculation, and 3.42 minus 0.5, that means you are going to get 2.9, yeah, right, 2.92 you are going to get. So instead of 1.74 you are going to get 2.92 hs1, okay. So this is the distribution for q12, okay. So that you have to write it very clearly, and once you get the distribution, now what you can do here, it is at 1 2, at 1 you can consider s1 equal to 0, at 2 you can consider s1 equals to h by 2, okay. So at 1 s1 equals to 0, when you substitute s1 equal to 0 in this equation, you are going to get q1 equal to 0, and at 2 s1 equals to, you can substitute h by 2 because it covers a distance of h by 2, and you can substitute in this equation, and you are going to get q2 equals to 0.42 sy by h, okay. So this is what for the bottom flange 1 2. Similarly you have to consider the web, that is 2c, okay, and when you try to consider the web, here you consider the 2 3, okay, but you can consider 2c, no problem. And or you can consider 2 3 web. This is centroid, and you can consider this as S2 distance. Okay, and again, so better to go with instead of 2 3, better to go with 2C because of symmetry. You can write, and you can go to consider S2 as the distribution and its x distance. So x distance from here to here, because you are calculating the vertical panel length and there is no x distance, so you straight away you can consider x equal to 0 here, and its y distance from here to here you have to measure. So first of all, it is below the centroidal axis, so that is minus and total distance is h by 2, and h by 2 you have to subtract s2, so then only you are going to get this distance. So minus h by 2, so you can substitute y equals to s2 minus h by 2 as the distance, and take this and substitute in the equation for 2 3. So when you try to substitute in this equation for 2 3, so 2 3 equals to sy by h cube integral 0 to s2 10.28 10.32x. So 10.32 x is 0 minus 6.84 y is s2 minus h by 2 into ds2, for which you need to add the open section shear flow also, that is nothing but q2. Okay, starting shear flow you have to add, that is q2 you have to add for this one. But what is q2? We got from the previous expression, q2 we got it as 0.42 sy by h, so that we have to add here. So q2 0.42 sy by h, that you have to add. Okay, so this again you have to integrate, so this straight away goes to 0, so you left with sy by h cube, and here integral 0 to s2, and what you are going to get, minus 6.84 s2 plus 6.84 h by 2 into ds2 plus 0.42 sy by h. So this is what you are going to get. And now after this, the integration, you are going to s2 integration becomes s2 square by 2, and h by 2 integration you are going to get h by 2 into s1. Okay, so that you have to write. I am writing over here. So that is equals to sy by h cube into minus 6.84 into s2 square by 2 integration plus this 6.84 by 2, it becomes 3.42 into h into s1. Okay, so this is integration plus 0.42 into sy by h, that is a q2. Okay, so after this is nothing but what, q2c. Now once you got the distribution, now you have to apply the boundary conditions at 2, and at 2 the position of s2 equal to 0. Substitute in the above equation. S2, if you 0 you substitute, this term goes to 0, and this term, this is also s2, this term goes to 0, and you left with only this one. So 0.42 sy by h, which is nothing but q2, same like the previous one. Okay, so that is what important. Now if you want to calculate at c, you have to substitute s2 equals to h by 2, because that is the distance h by 2. So when you try to substitute in place of s2, h by 2 whole square, so here you are going to get what you are going to get here, sy by h cube minus 3.42 into s2 square, that is h square by 4 plus 3.42 h into s2 is nothing but again h by 2. Okay, plus 0.42 sy by h. Okay, now this you need to calculate it. Okay, so from this let's try to calculate that also, and so that it will become easier for you to understand. Right, now this qc, that is equals to sy by h cube, and I am taking h square common here, so h square common, and minus 3.42 by 4, so that is minus 0.854 0.855. So h square already we took common, and this you get this one, and plus here you are going to get 1.71 plus 0.42 sy by h. So this h square and h cube gets cancelled, and you get 1.71 minus 0.855, and 1.710 0.855. If you try to substitute this 5 and 5, and here, so you are going to get 0.855 sy by h plus 0.42 sy by h. Okay, so together at QC you are going to add 0.420 and 5721. So you are going to get 1.275 sy by h. So that is QC. Okay, so in the distribution here, how to represent this one? How to represent? So at 1, shear flow is 0. At 2, the shear flow is 0.42 sy by h. Okay, and at C, the shear flow is 1.275 sy by h. So similarly, at 4, the shear flow is 0, and at 3 again you can consider that is 0.542 sy by h. Okay, and it will be similar. Okay, so is going to take the linear curve from here to here, and going to take linear curve from here to here, and if, you can consider here, and you'll get a distribution like this here. Okay, so here also you are going to get C also 1.275. So this is how we calculate the shear flow distributions at 1, 2 and C that we have seen here, and then probably the shear flow distribution looks like here. Okay, and 2, 3 distribution you will get h square, and so that it will be parabolic, and so that 1, 2, 3 here you may get linear here, but 2, 3 you are going to get parabolic curve. So this is what the parabolic curve which we have seen. Okay, so that is how we find out the shear flow distribution for open section beams using the formula for shear flow. Okay, so thank you everyone for watching, and the next class we see the shear flow in closed section beams as well. Thank you.